This diagram illustrates the hierarchical directory structure for a Tessent SSN, streaming scan network, workflow in a multi-block design. The top-level directory contains subdirectories for wrapped cores like processor core and GPS baseband, each with their own DFT insertion steps. Each block follows a consistent flow, starting with memory BIST insertion, followed by SSH, EDT-OCC, synthesis, scan chain insertion, post-synthesis TIDB view creation, ICL pattern verification, and a TPG pattern generation. This modular approach enables parallel processing of individual blocks. The top-level directory includes additional steps not present in subblocks, such as retargeting of TPG patterns and failure diagnosis, indicating final system-level DFT tasks. The RTL folder under each block holds the original RTL code, while the library folder likely contains shared IP or test infrastructure. This diagram illustrates the Tessent SSN workflow for hierarchical designs, starting with two sequential DFT insertion passes. The first pass focuses on memory built-in self-test, while the second integrates EDT, OCC, and SSN features. These steps ensure comprehensive testability at the block level before synthesis. After the second DFT pass, synthesis is performed, creating both stitched and unstitched scan chains. Stitched chains are used to generate a TSDB view, which captures the post-synthesis test structure. This view is critical for accurate pattern generation and verification. Unstitched scan chains proceed to Tessent scan insertion, followed by ICL-based pattern verification to validate test patterns against the synthesized design. Finally, a TPG generates the full set of test patterns, ensuring high fault coverage across the entire block. This diagram illustrates the hierarchical structure of a Tessent DFT flow with SSN, streaming scan network, integration. At the top level, the flow is named Tessent example hierarchical flow with SSN version year.quarter greater than, indicating a versioned example design. The flow contains wrapped cores, which are individual blocks in a hierarchical design. Each wrapped core includes a processor core, representing a functional block that undergoes DFT. This diagram illustrates the hierarchical structure of a design with streaming scan network, SSN, elements inserted at different levels. The top-level module, wrapped cores, contains two subblocks, processor core and GPS baseband. Within each block, SSN-related logic test elements are inserted using the insert SSH EDT OCC command. The numbering indicates the order of insertion, first in GPS baseband, then in processor core, showing a bottom-up approach to SSN integration. The SSN wrapper is applied at the block level, enabling automated connections between SSH, EDT, and OCC components when using process DFT specification. This ensures proper IJTAG access and data path continuity across the hierarchy. This diagram illustrates a hierarchical DFT flow with Tessent SSN insertion, showing how different design blocks are processed in a structured manner. The top-level module, Tessent example hierarchical flow with SSN v-year.quarter, contains two main subblocks, processor core and GPS baseband. Each block undergoes synthesis with RTL-level DFT insertion, as indicated by the synthesize RTL steps. The processor core uses step 3, synthesize RTL, while GPS baseband uses step 2, synthesize RTL, suggesting a staggered or prioritized synthesis order. This diagram illustrates a hierarchical DFT flow using Tessent's streaming scan network, SSN, in a multi-block design. The top-level module, Tessent example hierarchical flow with SSN v-year-quarter, contains two main submodules, wrapped cores and GPS baseband. The wrapped cores block includes a processor core that has undergone post-synthesis scan insertion, as indicated by the for-alt create post-synthesis TSDB view command. This step integrates the scan-inserted netlist with RTL-level DFT collateral into a unified TSDB view. Similarly, the GPS baseband block uses 3-alt create post-synthesis TSDB view to consolidate its own scan-inserted netlist and DFT data. This approach enables consistent DFT verification across hierarchical blocks while maintaining traceability and automation through the TSDB framework. This diagram illustrates a hierarchical DFT flow using Tessent Streaming Scan Network, SSN, in a multi-block design. The top-level module, Tessent example hierarchical flow with SSN v-year.quarter, contains two wrapped cores, processor core and GPS baseband. Each core has its own scan insertion step, indicated by the numbered insert scan tasks. The forward insert scan under processor core suggests it is processed later in the flow. possibly due to dependency or timing constraints. Similarly, 3-insert scan for GPS baseband indicates an earlier insertion step. In SSN flows, scan chains are inserted at the block level and connected through wrapper chains to EDT controllers. This enables efficient test data streaming across hierarchical boundaries, reducing test time and improving controllability and observability. This diagram illustrates a hierarchical DFT flow using Tessent Streaming Scan Network, SSN, in a multi-core design. The top-level module, Tessent Example Hierarchical Flow, with SSN v-year.quarter, contains two main blocks, wrapped cores and GPS baseband. The wrapped cores block includes the processor core, which runs the 5 verify ICL-based patterns step. This step verifies the ICL-based patterns after synthesis, ensuring proper connectivity through the IJTAG infrastructure. Similarly, the GPS baseband block executes 4 verify ICL-based patterns, confirming ICL model integrity at the subblock level. Both verification steps are critical when using SSN because they validate the continuity of the scan network and ensure that the test setup remains functional post-synthesis. These checks must be completed before a TPG and scan retargeting can proceed. This diagram illustrates the hierarchical flow for generating a TPG patterns in a Tessent SSN streaming scan network environment. The top-level design contains wrapped cores, each of which may include processor or baseband blocks. Within each core, the ATPG pattern generation step is executed independently. For example, the processor core runs 6.generate ATPG patterns, while GPS baseband runs 5 generate ATPG patterns. This reflects the modular nature of hierarchical DFT flows. The numbering indicates the sequence of operations, suggesting that pattern generation occurs after scan insertion and graybox model creation. Since SSN integration happens at the block level, these steps are performed within each wrapped core, using the pre-generated scan graybox models. This diagram outlines the top-level DFT insertion workflow for hierarchical designs using Tessent tools, focusing on streaming scan network, SSN, integration. The process begins with 2 sequential DFT insertion passes. The first targets memory BIST and boundary scan, while the second adds EDT, OCC, and SSN structures. These steps ensure comprehensive test infrastructure is in place before synthesis. After DFT insertion, synthesis occurs, creating either stitched or unstitched scan chains. Stitch chains proceed to TSDB view creation, which captures the post-synthesis design state for further analysis. Unstitched chains go directly to Tessent scan insertion, where scan chains are formed and optimized. Following scan insertion, ICL-based pattern verification ensures compatibility between pre- and post-synthesis test patterns. Then, a TPG generates test patterns, which are later retargeted to account for any structural changes introduced during synthesis. This workflow enables efficient test generation and verification in complex hierarchical designs. This diagram illustrates the top-level hierarchical flow for Tessent SSN, streaming scan network, insertion. The structure shows a top-down approach where the top module contains the primary DFT insertion step. The first step, labeled 1 insert BS scan, represents the insertion of boundary scan logic at the top level. This step is critical for establishing the SSN bus connections and clocking infrastructure across hierarchical blocks. In this flow, auxiliary pins are used to connect the SSN bus and bus clock instead of EDT channels, enabling efficient test patterns streaming through the design hierarchy. This diagram illustrates the hierarchical DFT flow for inserting streaming scan network, SSN, elements at the top level of a design. The process begins with the top-level module, where SSN components are added during the second DFT insertion pass. The step labeled 2.insert SSH EDT OCC represents the insertion of SSH, EDT, and OCC elements at the top level. These components are automatically connected by the tool when using the process DFT specification command, ensuring proper signal routing. The DFT specification defines the physical order of lower-level cores along the SSN data path, from bus in to bus out. SSN nodes like pipeline, multiplexer, or bus frequency divider can be specified in this order to control scan chain topology. This diagram illustrates a secondary data path in a streaming scan network, SSN, configuration, where multiplexers are used to selectively route scan data through or around the GPS baseband blocks. The RX1 pipe connects to the input bus, feeding into GPS1 and GPS2, which represent physical blocks in the design. A MUX node is placed after these blocks to allow bypassing them during scan testing. When the MUX selects the 0 feet path, it routes the signal directly from GPS 2 to processor 1, effectively excluding the GPS blocks from the scan chain. This enables independent testability of the processor core while maintaining scan continuity. The SSH block represents the SSN interface that manages the scan chain control and synchronization. The O pipe outputs the final scan data to the bus out. This setup supports hierarchical DFT by allowing different configurations of the multiplexers to be verified using procedure step wrappers and continuity patterns. This diagram illustrates the hierarchical flow for top-level streaming scan network, insertion in Tessent. The structure shows a directory path leading to the synthesis step, specifically targeting the top module. The top folder contains the synthesize RTL design after DFT insertion. The file 3.synthesize.rtl represents the synthesis step, where the DFT-enhanced RTL is processed to generate a netlist suitable for downstream physical implementation. This step is critical in hierarchical designs, as it ensures that the streaming scan network and other DFT structures are properly integrated at the top level before moving to block-level scan chain insertion or post-synthesis TSDB creation. This diagram illustrates the hierarchical flow for creating a post-synthesis TSDB view at the top level in a Tessent SSN workflow. The top-level design, represented by top, is the root of the hierarchy where the TSDB view is generated. The script for alt create post-synthesis TSDB view is executed to generate the TSDB view after synthesis. This step is critical for capturing the scan chain structure and timing information from the synthesized netlist. Unlike block-level creation, the top-level process also requires opening the TSDB to child blocks, ensuring full visibility across the hierarchy. This enables accurate ATPG pattern generation and verification across all levels. This diagram illustrates the hierarchical structure of a Tessent SSN flow, focusing on the top-level design. The root node represents the main design hierarchy, labeled with a version naming convention that includes year and quarter placeholders. The top block is the primary module where scan insertion occurs at the top level. This is critical for managing scan chains across hierarchical blocks in a design. Underneath top, the for insert scan step indicates the specific phase where scan chains are inserted using Tessent scan tools. This step aligns with a post-synthesis TSDB creation and ensures proper timing and connectivity for test patterns. This diagram illustrates the hierarchical structure of a Tessent SSN workflow for top-level scan insertion and verification. The root directory represents the main project hierarchy, organized by year and quarter, indicating a version-controlled flow. The top folder contains the top-level design where SSN is applied. Within it, the 5.verify ICL-based pattern script is highlighted as a key step in verifying ICL-based patterns after synthesis. This step ensures that the ICL network remains functional post-synthesis, enabling reliable ATPG and scan retargeting. The verification process at the top level mirrors the block-level approach but requires opening TSDB files for child blocks. This allows consistent pattern simulation across hierarchical levels while maintaining isolation through pre-connected boundary scan chains. This diagram illustrates the hierarchical flow for generating a TPG patterns at the top level in a Tessent SSN-based design. The top directory represents the top-level module where a TPG patterns are synthesized. The step labeled 6.generate a TPG patterns indicates the final stage in the workflow where test patterns are created using the scan gray box views of lower-level blocks. These blocks operate in external mode during top-level ATPG generation. To ensure timing consistency across all blocks, the timing options from each block must be imported to determine the maximum TCK period. This ensures that generated patterns meet the performance requirements of all submodules. This diagram illustrates the hierarchical flow for retargeting a TPG patterns using Tessent's streaming scan network, SSN. The top-level directory contains the main workflow, with a specific focus on the retargeting step. The 7 retarget a TPG patterns folder represents the core step where a TPG patterns from individual blocks are retargeted to the top level. With SSN, this process is simplified because there's no need to configure scan modes at the top level. Instead, the ADD core instances command specifies which block modes to target. This approach allows for flexible and efficient test pattern generation. Engineers can retarget one block at a time during DFT sign-off to speed up simulation, or multiple blocks in parallel for manufacturing, without hard-coding block groupings at design time. This diagram illustrates the two-step Tessent diagnosis workflow for hierarchical designs using streaming scan network SSN patterns. First, SSN patterns are run on the tester to generate failure files. These failure files are then reverse mapped using top-level pattern information and STYL data to align them with core-level patterns. Next, the mapped failure files are fed into Tessent diagnosis along with a core-level flat model and pattern database (PATDB). This step enables precise fault localization by correlating failures to specific design elements. The output is a suspect report listing potential root causes of the observed failures. This diagram illustrates the hierarchical structure of a Tessent SSN workflow example, specifically showing how the top-level design contains a failure diagnosis module. The path indicates that this is part of a larger test flow focused on diagnosing faults in scan-based designs. The directory structure reflects a modular approach where top represents the main design hierarchy and 8 failure diagnosis is a submodule dedicated to fault analysis. This organization supports scalable test development across complex chip designs. In practice, this structure enables targeted simulation and fault injection using serial scan patterns, as described in the manual. The naming convention includes year and quarter placeholders, suggesting versioned or time-based test case management. This diagram illustrates the streaming through IJTAG mode, a fail-safe method for delivering scan data when SSN data path timing issues occur. Scan data enters via the IJTAG interface and is routed through static registers controlled by an FSM and clock generator. The IJTAG network uses a two-edge timing scheme, making it robust and always accessible through the standard JTAG TAP. Data flows from bus in through the bus in reg, passes through internal logic blocks, and exits via bus out reg to the output bus. Key signals like scan-in, EDT update, and shift cap clock are generated by the clock generator block and synchronized with the IJTAG clock TCK. The loopback path enables testability verification, while the register block supports scan chain operations. This mode supports multiple channels and parallel testing in complex designs. This diagram illustrates the on-chip comparator logic used in Tessent's streaming scan network SSN for hierarchical designs. The comparator checks scan output against expected values, with masking and comparison enable signals controlling the process. Two exclusive or gates compare from scan-out signals with expected values, producing SSN0 signals that are then gated by mask and CMP enable conditions. The blue highlighted logic represents optional sticky status resolution circuitry enabled when the property sticky status resolution is set to output chain. This includes D flip-flops and multiplexers that capture and route status bits through the SSN bus. The select sticky status signal determines whether the current or previous status is passed forward. The final outputs, JTAG status 0, JTAG status hash, SSN status 0, and SSN status hash, are derived from these comparisons and control signals. These signals feed into the SSN network to report test results. The clear status and enable sync inputs allow synchronization and reset of the status chain, ensuring accurate fault detection during scan testing. This diagram illustrates the streaming scan network, SSN, data path within a tiling architecture. The chip is divided into multiple Core A tiles arranged in a grid, with a central Core M and Core T Core B modules forming a vertical backbone. The blue loops represent the SSN data paths that traverse horizontally across the Core A tiles and vertically through the Core M module. These paths enable high-speed scan data transfer between test logic and the tester. To minimize loop delay, the design uses a local clock tree around Core M to retime data before it exits the chip. This reduces the impact of global clock tree delays, allowing reliable operation at higher frequencies, like 200 MHz or 400 MHz with frequency dividers. This diagram illustrates the clock tree stepping down in the final stage of a streaming scan network, SSN, pipeline. The SSH and SBFD blocks, each with 32-bit scan chains, feed into a 64-bit SO pipe stage. These components are within the CTS region, indicating they are subject to clock tree synthesis constraints. The SO pipe stage uses a 2/2 scan configuration, meaning 2 scan cells per bit position, enabling efficient data shifting. The loop timing 1 and loop timing 2 annotations highlight critical timing paths that must be analyzed for proper scan operation. Data flows from the SSH and SBFD stages through the SO pipe to produce data out. Clock in drives the entire chain, but the clock is stepped down at the last pipeline stage to manage timing skew and ensure reliable capture. This technique is essential when multiple identical SSN data paths exist, allowing input broadcast to reduce test data volume and improve test efficiency. In normal SSN operation, packets can span multiple bus cycles and may rotate across the bus bits. This rotation occurs because the packet length isn't necessarily aligned with the bus width, leading to unpredictable mapping between data outports and SSHs. For example, a 9-bit packet over an 8-bit bus causes bit positions to shift across cycles. To disable this rotation, Tessent adds padding to make the packet length a multiple of the bus width. In this case, a 9-bit packet becomes 16 bits, 2 full bus cycles. The padding ensures consistent bit alignment across cycles, enabling predictable mapping from top-level ports to SSHs. The figure shows how the same data is mapped differently in normal mode versus padded mode. Without padding, bits like a 5-2 appear in cycle 5, but with padding, they are delayed and aligned consistently. This predictability is critical for hierarchical scan testing, where test patterns must be accurately routed. This diagram illustrates the standard procedure flow for a streaming scan network, SSN pattern. The sequence begins with test setup, which initializes the test environment and configures scan chains. Next, SSN setup prepares the SSN infrastructure, enabling data streaming between scan cells. This is followed by test payload, where the actual test vectors are applied to the design under test. This diagram illustrates the sequence of procedures used when generating SSN patterns with the max loads option. The flow begins with test setup, which initializes the test environment. Next, SSN setup configures the streaming scan network for data transfer. The core of the test is the test payload phase, where actual scan data is applied to the design. Following the payload, SSNN finalizes the network state, and testN concludes the test session. These steps are duplicated across all pattern files when using write patterns with max loads. This diagram illustrates the structure of SSN, Streaming Scan Network, test patterns for hierarchical chip designs, where test procedures are split into separate files to optimize tester efficiency. Each chip's test flow includes test setup, SSN setup, test payload, SSN end, and test end phases. The test payload contains 50 scan loads as specified by the max loads option. By separating these procedures into individual files, write enable reduce overhead from repeated setup operations, allowing more tester time to be dedicated to actual pattern application. This is especially beneficial in large-scale manufacturing tests, where setup time can dominate overall test duration. It's critical to maintain the correct order when applying these separated files on the tester. Any deviation may cause mismatches on the SSN bus output. Additionally, all write patterns commands must use consistent parameters like begin, end, and pattern sets to ensure proper synchronization across chips. This diagram illustrates the sequence of STYL pattern files applied during a Tessent SSN-based test flow. The process begins with test setup.still, which configures the initial test environment. Next, SSN setup.still initializes the streaming scan network infrastructure. These two setup files can be combined using the -all setup only option to reduce file count. The payload files payload1.still through payloadn.still contain the actual scan loads and are grouped with both test payload and SSNN procedures. Finally, testn.still concludes the test sequence by executing the testn procedure. This diagram shows the correct order for applying SSN pattern files during manufacturing testing. The sequence starts with setup still, which initializes the test environment and configures the scan chains. Next, multiple payload patterns are applied, each containing up to 500 scan loads. Each payload is followed by an SSNN procedure to flush the network and prepare for the next pattern. These can be combined into a single file using the all-end only switch. Finally, testn still concludes the test by deactivating the scan network and resetting the system. This structured flow ensures reliable test execution in hierarchical designs. This diagram illustrates the correct sequence for applying STYL pattern files in a Tessent SSN flow with on-chip compare enabled. The order is critical because the SSN data stream depends on proper timing and initialization of the streaming scan network. The process begins with test setup still to initialize the tester environment, followed by on-chip compare self-test still to verify the on-chip compare logic before any payload patterns are applied. This ensures accurate comparison during scan testing. Next, SSN setup still configures the SSN infrastructure, then payload 1 still with 500 scan loads delivers the first test payload. Afterward, SSN end still terminates the current SSN session, followed by another payload end still, another SSN end still, and finally test end still to complete the test sequence. This diagram illustrates the correct sequence for applying streaming through IJTAG patterns during silicon debug. The order ensures incremental verification of the SSN functionality, starting with setup and ending with test completion. The process begins with test setup still to initialize the environment, followed by SSN setup still to configure the SSN network. Then payload 1 still applies a test payload, 500 scan loads, to verify data transmission through the network. After the first payload, SSN end still terminates the SSN session. This is repeated with SSN setup still and payload end still for additional payloads, ensuring consistent behavior across multiple cycles. Finally, test end still concludes the entire test sequence. This flowchart outlines the recommended order for applying test patterns to debug SSN, streaming scan network failures. It starts with ICL network verify patterns, which validate the accessibility and functionality of IJTAG registers in the SSN network. Next, SSN continuity patterns are applied to verify signal integrity and connectivity across the SSN links. These patterns ensure that data can be properly transmitted between SSH nodes without corruption or loss. Following that, on-chip compare self-test patterns are used to confirm the absence of stuck-at faults in the on-chip compare logic, including sticky bit status registers. This step ensures the integrity of internal comparison mechanisms. Finally, SSH loopback patterns are applied to test the loopback capability of SSH nodes, verifying that data sent through the network is correctly received and echoed back. This completes the incremental verification of SSN functional behavior. This diagram illustrates the correct sequence for applying STYL patterns to the tester in a hierarchical design using Tessent SSN. First, the test setup still pattern is applied. This pattern configures the test environment and initializes the ICL network, ensuring that all necessary scan chains and control signals are properly set up before verification begins. Next, the ICL network verify still pattern is applied. This pattern performs continuity checks across the streaming scan network SSN, verifying that each node and multiplexer branch is correctly connected and accessible from bus in to bus out. The diagram illustrates the correct sequence for applying STYL patterns to the tester in a Tessent SSN flow. First, the test setup.still file is applied to configure the test environment and initialize the scan infrastructure. Next, the SSN continuity.still pattern is applied to verify the integrity of the streaming scan network SSN connections between cores. This ensures that all scan chains are properly connected and functional before proceeding with more complex tests. This order is critical because the test setup must be complete before continuity checks can be performed. Applying these patterns in the wrong order may lead to test failures or incorrect diagnostics. The diagram illustrates the correct sequence for applying SSN on-chip compare self-test patterns to the tester. First, the test setup.still file is applied to configure the test environment and establish initial scan chain connectivity. Next, the on-chip compare self-test.still file is applied to perform the actual on-chip compare self-test. This pattern verifies the integrity of the on-chip compare hardware and sticky bit registers. This two-step process ensures that the test setup is properly initialized before executing the diagnostic test, which helps detect stuck-at faults in the SSH compare logic. This diagram illustrates the correct sequence for applying STYL patterns in a Tessent SSN workflow. The process begins with test setup still, which configures the initial test environment. Next, loopback still is applied to verify the SSH network's ability to reliably transmit packetized data without involving EDT or scan chains. Following the loopback test, SSN end still is used to properly terminate the SSN configuration. Finally, test end still completes the test sequence by finalizing the test setup. This order ensures that the SSH network is validated before any payload-based tests are executed. The grouping of patterns into logical phases, setup, loopback, end, ensures robustness and traceability during manufacturing testing. By isolating SSH functionality early, engineers can quickly identify network-level failures before proceeding to more complex scan chain tests. This diagram illustrates the correct sequence for applying STYL patterns in a Tessent SSN-based DFT flow. The order ensures proper setup, payload execution, and cleanup of scan chains across hierarchical designs. The process begins with test setup still to initialize the tester environment, followed by loopback still to configure SSH loopback paths. Then SSN setup still prepares the streaming scan network infrastructure before executing test payloads. Payloads like chain still and scan still are applied next, each targeting specific pattern sets. After each payload, SSN still resets the SSN state. Finally, test end still concludes the test session. This structured flow prevents conflicts and ensures reliable manufacturing testing. This diagram illustrates a FIFO-based streaming scan network, SSN, configuration with a multi-clock path, MCP setup. Data enters the FIFO through the data in port and is stored across 4 stages labeled 1/4 to 4/4, which represent sequential pipeline registers. The data flows from these stages into a MUX controlled by the MCP logic, allowing for timing alignment between different clock domains. The output is driven by outclock and appears on data out, synchronized via the data path bus data out star signal. The in clock drives the input side of the FIFO, while the out clock governs the output side. This structure enables DESQ control in hierarchical designs, supporting flexible scan chain routing across clock domains. This diagram illustrates the clock signal generation for Tessent's streaming scan network, SSN, in hierarchical designs. The primary input is the test clock, which drives multiple derived clocks through gating and division logic. Key signals include shift capture clock gated, EDT clock gated, and their divided versions, all synchronized to ensure proper scan operation. The red cells represent persistent cells that maintain state across scan operations. Bypass mode clocks, in brown, are optional and used for test flexibility. All generated clocks are defined on pins of these persistent cells, ensuring predictable timing behavior during testing. Clocks prefixed with Tessent are automatically generated by the tool, while SSH-generated clocks use the format Tessent SSN. These clocks are physically exclusive, meaning only one can be active at a time. The speed relationships show that the bus clock runs at maximum speed, while scan clocks are derived from it via division or gating. This slide outlines key clock constraints for Tessent Streaming Scan Network. Tessent Streaming Scan Network in hierarchical designs. The first constraint ensures that fast and slow scan clocks are mutually exclusive, preventing simultaneous operation which could cause timing conflicts. The second constraint enforces physical exclusivity between SSH internal mode and bypass test modes, ensuring these modes do not activate simultaneously. This is critical for avoiding signal interference during test operations. Finally, the asynchronous relationship between scan clocks and all other clocks is defined. This allows scan clocks to operate independently, enabling proper scan chain functionality without affecting functional clock domains. This diagram illustrates the SSH, streaming scan network circuit that generates the scan-en and EDT update control signals. The scan-en signal is derived from a D flip-flop triggered by the Tessent SSN bus clock star, enabling scan operations in the design. The EDT update signal is generated using 2 flip-flops, a posage-triggered flop, labeled 2, and a neg-edge-triggered flop, labeled 3. When the bus clock period matches the scan clock period, the neg-edge flop ensures proper retiming for the EDT controller's posage flops. When the EDT clock is divided, the posage flop 2 toggles EDT update at the correct timing relative to the destination flop, ensuring reliable data transfer. This dual-path logic supports both synchronous and divided clock scenarios in hierarchical designs. This diagram illustrates the timing margins for the scan-enable signal in a streaming scan network, SSN design. The scan-enable signal controls the loading and unloading of scan chains, and its timing relative to the shift cap clock and EDT clock is critical for reliable operation. The green annotations show setup and hold time margins for both positive and negative edges of scan-enable. For example, SE setup POS and SE hold POS define the required setup and hold times before and after a rising edge of scan-enable. These margins are derived dynamically from clock ratios and TCL variables in the Tessent SDC file. Notably, the scan-enable signal benefits from a half-cycle bonus when transitioning, because the first falling edge of the SCC clock occurs after the first rising edge. This improves timing safety compared to signals like EDT update, which relies on neg-edge flops and has tighter constraints. This waveform diagram illustrates the timing relationships in a streaming scan network, SSN setup. The bus clock drives the scan operation, with the ET update signal controlling when data is captured into scan chains. The gated scan clock is derived from the bus clock and synchronized with scan enabled to enable scan capture. The shift capture clock is a divided version of the bus clock, used for slower scan operations. It has a non-50 duty cycle due to the frequency ratio, as seen in the waveform. This allows for precise control over scan timing under different clock conditions. The signals to scan in and from scan out represent data flow through the scan chain. The timing constraints shown in the tShell script ensure proper setup and hold times between EDT update and the divided clocks, preventing metastability and ensuring reliable scan capture. This waveform diagram illustrates the timing behavior of a scan chain interface under gated clock conditions, where all extra cycle variables are set to 0. The bus clock and EDT update signals drive the scan operation, while scan enable enables the scan mode. The shift capture clock is derived from the bus clock and used for shifting data through the scan chain. The toScan-in signal shows data being shifted into the chain during the active phase of the shift capture clock. The from-scan-out signal reflects the output data, which is synchronized with the capture edge. Note that the scan-enable signal has setup and hold margins relative to the gated clocks due to internal SSH logic requirements, providing additional timing robustness. This configuration ensures proper timing alignment between the scan-enable and the clock edges, minimizing metastability risks. The absence of extra cycles simplifies timing analysis but requires careful constraint management in the design flow. This waveform diagram illustrates the timing behavior of a scan chain interface under gated clock conditions, where all extra cycle variables are set to 0. The bus clock and edit update signals show regular clocking patterns, while the scan-enable signal is gated, enabling scan operations only during specific intervals. The shift capture clock is derived from the bus clock but is divided and synchronized to control scan shifting. The two scan-in and from scan-out signals represent data flow through the scan chain, showing how data is captured and shifted in sync with the scan-enable and shift capture clock. Note that due to internal SSH logic requirements, the setup and hold margins for scan-enable are enhanced compared to standard gated clock scenarios, providing better timing robustness. This is critical for reliable scan testing in hierarchical designs. This waveform shows a gated scan clock scenario where the scan-enable signal controls the enable of the shift capture clock. The bus clock and EDT update are synchronized to the main clock domain, while scan-enable is used to gate the scan operation. The shift capture clock is derived from the bus clock but only active when scan-enable is high, creating a pulsed clock for scan shifting. This gating reduces power during normal operation and ensures proper timing margins. The two scan-in and from scan-out signals show data movement through the scan chain. The timing relationship between scan-enable and the capture edge is critical for setup and hold compliance in hierarchical designs. This diagram illustrates the streaming scan network. Scan chain interface circuit, which manages scan operations in hierarchical designs. The circuit includes clock gating and division logic to support both normal and divided shift clocks during scan mode. The red bordered cells are persistent, meaning they retain their state across scan cycles. The green elements activate only during scan with gated shift clocks, while blue elements operate under divided shift clocks. These color-coded components help distinguish functional modes. Scan data flows from the streaming scan network through to scan-in pins into the scan chains on the right, with outputs returning via from scan-out pins. Direct loopback paths allow test data to bypass certain logic in specific modes, improving test efficiency. This diagram illustrates the localized scan timing in a hierarchical design using Tessent's streaming scan network, SSN, with shift-only mode, OCCs. The scan host node generates key DFT signals, scan-in, EDT clock, EDT UPD, and shift capture clock, based on the bus clock. These signals are distributed to both internal and external EDT channels, enabling consistent scan control across the hierarchy. The OCCs, on-chip clocks, receive functional clock 1 and functional clock 2 as functional clock inputs. During external scan modes, when scan-in is high, inactive OCC still inject the shift capture clock from the local scan host into their respective clock domains. This is enabled by the shift-only mode feature, ensuring that shift timing remains fully derived from the SSN bus clock, improving timing closure. Even when OCCs are not active during external test modes, they must pass through the shift capture clock generated by the scan host. This allows the entire shift operation to be internally managed within each block, decoupling it from external timing constraints and simplifying design verification.